Good afternoon, everybody. Continuing story of MSc students doing great things is about to start. So this afternoon, first off, we have Stephen Mills, who has finished his work on the 60-point, 600-hour project for his Master of Space Science in Technology. This afternoon, Stephen is going to introduce you to the concept of the Lomb-Scargle periodogram. Now, don't get too scared by that because it's Fourier analysis with knobs on. It's a powerful tool for finding the frequency components of irregularly sampled data, such as exoplanet TTVs. He's applied the method to results published in Exoclock Data Release 3. And just in case any of the audience are not too familiar with Exoclock, let's quickly tell you what that is. Exoclock is a pro-am collaboration, professional amateur astronomer collaboration, with the aim of improving the ephemerides, to pronounce it correctly, of exoplanets, which will be the targets of ESA's aerial mission due for launch in 2029. Ariel, the spacecraft, the space telescope, will need to point at hundreds of host stars at exactly the right time to catch the transits of exoplanets so that the instrumentation on Ariel can do transmission spectroscopy observations of these interesting planets' atmospheres. So it's all down to the amateurs feeding the data into the Exoclock collaboration and coming out with big improvements in the ephemerides, which will allow Ariel to point in the right direction at the right time. So, Stephen, the floor is yours, or at least the screen is anyway.
Thank you, Rodney. So hopefully people can see my screen.
Yeah.
So I'm going to talk a bit about the analysis of periodic variations in exoplanets. And as Rodney said, that's involved the Generalised Lomb-Scargle periodogram, which I'll give a few examples of. I kind of wanted a subtitle for the talk, and you can see it there, of how I went looking for exoplanets and found variable stars. Because what I was trying to do was look for periodic TTVs that were telltale markers of other planets, as I think you heard about in some of the talks this morning. I didn't find any of them, but I did find some interesting things around variable stars. So that's what I'm going to talk about. A little bit about me. You've heard most of this. So I'm Stephen Mills. I retired from a career in IT a few years ago. And as Rodney said, I've just completed my MSc project. What I want to talk about is, you can see in the agenda there, a very little bit about Exoclock, because Rodney's just talked to you about it. A overview at a very high level of what a generalized Lomb-Scargle periodogram is and what it does. Then talk a bit about what I found both in periodic variations in transit timing, so TTVs, but also some periodic variations that I found in RP over RS. Whoops, sorry about that. Then I'll talk a bit about the interesting example I found in Kelp 9b, and if I've got time, I'll talk a little bit about Koi 13b, which also has some interesting things, but if I run out of time, I might skip that one. So I think Rodney covered most of the top bit of this slide about what Exoclock is. I think the interesting point is the point in the middle of the top half. So it's taking data from a huge number of sources, both amateur observations, the Exoclock Transit database, and space missions. So the Exoclock database contains lots of information from the Kepler and TESS satellites. And in fact, most of the interesting results I found came from the Kepler and TESS data. It does periodic data releases. So data release 3 was released in the back half of last year and contained data up until the end of 2021. And that's the set of data I used. And that covered about 450 exoplanets and had over 18,000 transit observations in it. And there's a quick summary of what I was doing in my project down in the bottom half. So I was actually taking some transit observations using the Open University's telescopes. And in fact, the one on the top right hand of the slide for HAT P21b is an observation I took using the Open University's telescopes in Tenerife and submitted to Exoclock. Then looking at the causes of transit variations, such as other planets, and I think Roger and Rodney gave you a summary of most of those this morning. And then I looked at methods to analyze the data on transit variations, mainly the generalized Lomb-Scargle periodogram, although there are other things as well. And then I analyzed the DR3 data using those methods. So a little bit about the generalized Lomb-Scargle periodogram. So what this method is trying to do is it's trying to look for periodicities in discrete data sets. And it's based on Fourier transforms, but it can handle regularly spaced data and non-regularly spaced data. So it's particularly good for this sort of exoplanet analysis, because you get some transit observations, but you don't get all of them. So you get irregularly spaced data. What you see on the left-hand side of this slide is the O-C, so the variation in transit time for the planet Kepler 18d. And I've used this one as the example because it's a very regular TTV caused by two exoplanets which are in resonant orbits. So the ratio between the orbits of Kepler 18c and 18d are almost exactly 2:1. So you get this very regular variation in the transit timing, as you can see on that graph. So what a periodogram does, and there's one on the right here for that data, is it basically looks across the range of periodicities and tries to see if there is a regular variation with that period. So on this one here, you can see the periodicity is along the x-axis. The y-axis is the power of the periodicity, and basically the higher the power of the periodicity, the more likely there is for a periodic variation. And if you sort of compare look at the left-hand side, you can kind of see that that varies every somewhere around just less than 20 epochs or orbits. And if you look on the right-hand side, that peak in the periodogram is around 17 and a bit, actually. So it very clearly shows this periodicity. Now, this is kind of a noddy example. Most of the data sets you use aren't anywhere as clear as this, and you just can't see the periodicities from the data. But one useful way you can do it is if you wrap the data on top of itself with the periodicity you've detected, you can start to see the variation. And what I've done on this slide here is this is the same data that was on the left-hand side of the graph, sorry, the graph on the left-hand side of the previous slide, but wrapped every 17.81 epochs. And you can see the variation of the red dots, which basically follow that dotted line sine curve, which is the curve of best fit. So general methodology of this detection is get the data, run a periodogram. For interesting peaks, you can try and wrap the data and see if it matches the sine curve, and then you can use least squares curve fitting to find the curve of best fit. Okay, so that's the general method of using GLS, and you can use it on any data set. So I used it on both the transit times, but I also use it on all the other parameters as well, and found some interesting things going on with various radius variations as well. So what results did I find? As I said, I applied this to all the planets in the Data Release 3 from Exoclock, and interestingly, they also did that with the Data Release 3 paper. And this table summarizes the results. Now, before I go into the table, it's worth saying that when you use a single GLS periodogram, it gives or can give false positives based on noise and your sampling rate. But by calculating many periodograms where you vary things within the noise, you can get a much better result. So these results and the results in the DR3 paper use that technique. It does mean it takes up quite a lot of computing time. It ended up meaning that to do the GLS analysis on a planet took the order of hours. So my poor laptop was running overnight for quite a number of nights to do all this analysis. But what I came up with, all these planets here had periodicities detected using GLS. The box in the middle is ones where both myself and the DR Data Release 3 paper from Exoclock found periodicities. The ones in the left were in the Data Release 3 paper, but I didn't find them. And there's one on the right where I found a new one which wasn't in the Data Release 3 paper. So at first glance, you think it's quite good that there's lots of things in that middle box. But actually, when it comes down to detail, we were finding slightly different things. So all those ones I've highlighted in yellow, although both myself and the Data Release 3 paper in Exoclock found periodicities, we found different periodicities. And one of the reasons for that is there are lots of options and lots of ways you can implement the periodogram, and changing those options changes the results you get. It is worth saying, though, that all these results are at a 3 sigma level, which is a very high bar to meet to actually claim a detection. So basically, if you detect something with any of the options, in my view, that's a very worthwhile result and worth investigating. I did have some discussions with the Exoclock team, and for some of the ones in the left-hand column that I didn't detect, they actually forced into the analysis because they knew they had TTVs, so that explains some of them. And as I said, there was one there, COI13b, where I found a variation which wasn't in their analysis, which was quite good. So basically, that, although I didn't get exact results the same as the Exoclock team, it kind of validated what I was doing. And one of the things I wanted to try was find things that were nearly significant. So as I said, these are results you could find at the 3 sigma level, but I also looked at things that you could find at the 2.5 sigma level. And there's a number of planets there which I think are worthy of more investigation. They've all had about 40 transit observations or slightly more, but with even more observations, who knows what will happen? They could all move up to the 3 sigma level, which might detect some interesting variations, which might imply further planets. But as with all science, more investigation and more data is required. There is some extra data out there for most of these planets, which at some point in the future, I will add into the analysis and see what happens. And they would, as it says down the bottom, these would be good candidates for the Explore program. The one I'll draw your attention to in particular is Kelp 9b at the top. So although I didn't find TTVs at the 3 sigma level, there was TTVs at 2.5 sigma level with a periodicity of 3.2 epochs. And remember that number because it comes up in the next slide. So having done that with TTVs, I then thought, well, let's apply the same analysis to RP over RS, i.e. the ratio of the planet's radius to the star's radius. And I got lots of results. Unfortunately, most of them were false positives. I think Roger might have mentioned this morning, but the depth of a transit, which is directly related to RP over RS, depends on the wavelength that you observe the transit in. And in some cases where you had lots of observations at different wavelengths, that made the data look like sine curves to the periodograms. Generally, this was when 2 space missions had observed the same planet, so you could rule them out quite easily. I also found some more things that are worthy of further investigation, where you could find a variation in RP over RS, which was periodic, but only from one set of the data. So it was mainly the Kepler mission, which found some interest for which the data had some periodic variations in, but when you added all the other data in, it didn't come up with periodic variations. So not sure what was going on there, worthy of more investigation, as I said. But then Kelp 9b came up again. with a variation in RP over RS with a periodicity of 3.2 epochs, i.e. exactly the same periodicity as in the TTVs. And that graph there is the periodogram for that. It has an interesting sawtooth effect, but that comes from interference from two sets of data. Kelp 9b itself is quite interesting. It's the hottest known exoplanet, or at least was a few months ago. It's going around a rapidly rotating star, so you get an effect called gravity darkening. And it's kind of illustrated on the picture on the left-hand side. Because it's spinning rapidly, it has an equatorial bulge, and that equatorial bulge is at a lower temperature than the poles. Now, Kelp 9b itself is in a polar orbit, so its transit starts at the top, goes over the poles, and then goes down into the equatorial regions. And because it's hotter at the poles, there's more flux from the poles, and cooler at the equator, so less flux from the equator. So as it's transiting, it obscures less flux when it gets to the equator. Hence, you get a slope in the floor of the transit, which you can see in that thing in the middle. And some of these effects might be combining to give the results I saw. A couple other points to note about Kelp 9b, which I got from the literature, or one I got from literature. Kelp 9b is a variable star with a period of 7.59 hours. And that becomes very relevant to the data that I saw in a way I'll explain in a second. And as I mentioned, the data I was looking at mainly comes from space satellites. For Kelp 9b, all the data was from the TESS satellite. So, having found the variations, I then went to try and find the line of best fit. So, as I mentioned, the data comes from two data sets. One, I think, was 2019, one was 2021. And you can draw a line of best fit with a period of the 3.2 epochs, and you get a pretty good fit to the data in both the areas. However, it is worth noting that this periodic variation is quite small, so it's a 1.3% change in RPO over RS. And you can do the thing that I showed you in the earlier slides and wrap the data. So what we've got here is the data for RP over RS on the left-hand side, wrapped with a periodicity of 3.2. And what we've got on the right-hand side is the transit time data wrapped with the same periodicity. And you can certainly for the purple data, you can clearly see how it corresponds to that sine curve. For the right-hand side, it's not quite so good as you'd expect because it's only a 2.5 sigma result rather than 3 sigma on the left. But I think you can see certainly where the sine curve goes down, most of the data is below the axis, and where the sine curve goes up, most of the data is above the axis. It's quite interesting if you superimpose them, those two graphs, you get a graph like this, which seems at first sight to be pi by 2 out of phase, i.e. when the purple line is at the maximum is when the red line is crossing the axis. And there's a few other phenomena around exoplanets where you see two parameters pi by 2 out of phase. For instance, TTVs and TDVs caused by exomoons, for instance. So looks like there's something going on there. So I found these periodic variations. I knew there was a flux variation in the star, and I wanted to see if the two were related. And turns out the two are, well, numerically, the two could be related. So what I did is this is a graphical version of a bit of maths that I did. So we're looking at the flux variation. I said that's got a period of 7.59 hours. The exoplanet's period is 1.48 days, which is 35.5 hours. which is about 4.6 times the flux period. So on this graph, I've got the red line wiggling up and down is a representation of the flux of the star. And there's 4 to 5 peaks between each of the epochs or orbits. Now, what we're interested in is the flux at the point of transit, i.e., where is the red line at each of the integer values of epoch? And you get those dots, which at first glance doesn't look that interesting or that regular, but when you superimpose a sine curve with a period of 3.2 epochs, it's a precise fit. And you can go through the maths, and this is precisely what you'd get from a 7.59 hour flux variation. You'd get something with a period of 3.2 epochs. It's actually 3.198 or something like that. So what have we found? So for Kelp 9b, what I found was 2 periodic variations out of phase by pi by 2. It seems to be caused by this flux variation that goes on every 7.59 hours, and it says there that agrees to 0.3%. And although there's no readily obvious causal link between that flux variation and the variations I saw in the transits, the numbers are very, very close. So again, with all these things, more research necessary. Next thing to do would be to model the interactions of the flux variations and see how they could interact with the gravity darkening and things like that. And it depends on what the nature of the flux variation is. So if the star was actually pulsating, that could explain the variation in RP over RS, but wouldn't explain the TTVs. So as I say, more work to be done. I will do COI 13b very quickly because I'm running out of time. So the variation in COI 13b have many similarities with Kelp 9b. So COI 13b also, or COI 13 rather, also has gravity darkening. There are some periodic flux variations going on, but the maths doesn't quite work out as good. The O minus C variations are, you can kind of see it in that graph. And it's got some RP over RS variations as well, but not at the same period. So COI 13b is not quite a good set of result of Kelp 9b, but Kelp 9b is definitely a good result. So overall, what am I trying to say? Well, what I've been able to do is find 2 new periodic variation using publicly available data, using standard Python libraries. So I wouldn't call myself a professional coder, but I was able to write code bringing in those Python libraries to do the GLS analysis. And all I used was a fairly powerful laptop. There does seem to be a link between these variations and variations of flux of stars, hence my earlier comment on I went looking for exoplanets and found variable stars. And also found a number of variations that nearly meet the 3 sigma significance level. But more data and observations are required to see if I can bring them up or whether they disappear. And as it says there, there's lots of areas for further investigation coming out of this. So that's all I wanted to say, but very happy to take questions on anything.
I love students who finish with lots of areas for further investigation. Definitely scope for a PhD, and indeed you've outlined scope for others to follow in your footsteps and probably do broadly similar work on the ever increasing amount of data that we're getting.
Yeah.
So thank you very much. Well done.
Thank you, Robin.
Thank you, Stephen. If anyone has any questions, you can type them in the Q&A on Zoom.
Stephen, you mentioned that the planet was in a polar orbit as we see it.
Yeah.
And that there were variations in the diameter because of the fast rotation.
Yeah.
Does the rotation of the star link in any way to the variations in TTV, etc., etc.?
It wasn't immediately obvious. There is data on the rotation speed. I think it was every 14 hours or something like that, where there wasn't that direct mathematical linkage that I saw with the flux variation.
The reason I ask is that sometimes the star would appear to be broader than other times, depending on where it was in its rotations.
Yes. So, yeah, I think some of the examples you said earlier with sunspots and things like that can cause this sort of variation, but it wouldn't have the same period as I observed, I don't think. Again, it's all sorts of things to throw into the model.
We have some questions coming in thick and fast now, so we'll see how many we can get through, and if not, we can pick some up after three. So Seafried asks, how big would the size variations of Kelt 9 be according to the RP over RS variations?
So that's the 1.3% change. So the mean RP over RS is about 8%. And the actual size of the variations were about 1/10 of 1%.
And then Paul Dooley says, great work, Stephen. What other exoplanet parameters might be useful to have their periodicity examined?
So I did the periodicity variation. I tried it on TTVs, which are the main ones you do. I did it on RP over RS. I also did it on duration and depth. Now, interestingly, I think the way the Exoclock data is parsed means that duration variations are suppressed in their analysis. So I didn't find any duration periodicities where I would have expected to. And on depth, because depth is so closely related to RP over RS, you found the same sort of periodicities. So I'm sure there are other things you could try and do it on, but those are the ones I tried.
Then we have Jack asking, do you or have you looked at many more stars than the ones mentioned here? And did you find anything interesting in the data that you weren't expecting beyond the variations you've spoken about?
So I looked at all the 450 stars in DR3. There were some other interesting results, but not as so significant as the Kelt 9b ones and the Koi 13b ones. There were also some interesting things that had already been published. So I know Toy 216 has been mentioned, but from the data here, it looked like Toy 21602 was getting bigger. But I think it ended up being, one of the papers said the first set of data was a grazing transit and the transit had moved. So it was a full transit on the later data, which is why it looked like it became bigger. And there was this interesting thing going on in the Kepler data where there seemed to be periodic variations of RP over RS in the Kepler data, which would be worthy of more notes. And there's about, I'll say 10, it was somewhere between 5 and 10 planets that seemed to be happening.
We're just about at the time for Emily, but we've got two which might be quite quick questions to answer. Simon asks, have you published your results?
No, they're all in my submitted MSc project, and I better let Rodney mark it before it gets published.
And then Sigrid asks if there's any evidence for eccentric orbits.
I don't think I would have found any because, again, the Exoclock analysis, which is what I was using as a basis of my stuff, assumes the eccentricity, and for the vast majority of planets, it assumes that they got zero eccentricity, and so forces the data to fit that. So it would suppress any evidence.